Chapter 2, Section 2 starts off with three states of matter. We have gas, solid, and liquid, and I'm sure you've seen these three before, but perhaps you've never been described or explained why they are the way they are. If you look at this red dot with two blue dots, what you see here is an actual water molecule. Now, this is water in a gas form, and the reason why it's in a gas form is these water molecules actually vibrate. And if they have lots and lots of energy, like the ones in gas, they vibrate in a larger area. Let's say they vibrate within this box. So this water molecule will vibrate into this box, and what will happen is eventually they will bump in, this water molecule will bump into this one, and they'll push each other out of the way. And then this one right next to it might bump into its neighbor over here, and they'll push each other out of the way. And the result of all this pushing is that there's not a lot of water molecules in a gas form in this area. So when you go to a particular spot in the air and you're like, okay, let's see how many water molecules are there aren't many. If you took that same area, but instead of looking at the gas water, if you looked at the liquid water, you would see that there's a lot more water molecules here. And the reason is, instead of these water molecules, they have less energy. Instead of bouncing in a huge box, perhaps they'll bounce in that box. And when they bounce, they bump into each other, but they don't push each other as far, so more of them tend to gather together. And this is water in a liquid state. Now, water in a solid state looks less dense because you have these giant holes in the middle. And I completely agree with you. It does have giant holes in the middle like this. This is called a crystal structure, because if you look at this box right here, you can see that there's a hexagon in there. It kind of goes from here to here to here. This is called a crystal structure, and these water molecules vibrate as little as they possibly can. They don't even push each other out of the way. They just kind of vibrate in their little space, and they form these uniform structures like this. It's the same in every ice. If you look at every bit of ice, whether it's snow or an icicle, it doesn't make a difference. All the water molecules are lined up like this in these rings, and those are the three states of matter. Chapter 2, Section 2 covers energy in chemicals, and the energy of chemicals are found in their bonds. In general, just to keep it simple, the more bonds that a chemical has, the more energy it has. On these two pictures, you see energy, and as this energy rises up, what that means is whatever has more energy will have more and more bonds. So if you have something here, then that thing will have more chemical bonds than something like these products down here, which have fewer chemical bonds. Now, reactants are what goes into a reaction. The reaction does its work, and what comes out are products. And as you can see here, the reactants have more energy than the products. So the reactants have more bonds than the products, because we talked about that the amount of energy in a chemical is found in its bonds. So if the reactants have more bonds than the products, what we're doing here is breaking bonds. This thing has some number of bonds, we're breaking some bonds, and then these are the products. Also, in this picture to the right, where we have the reactants, they have a certain number of bonds, same as the other reactants. It just so happens this is going through a different reaction. Now look what happens. We have a certain number of amount of energy, but the products have even more energy. So in this reaction, we are forming new bonds. We're adding atoms to this chemical to make it larger. And this is a way of energy absorbing reaction where energy is being put into the product by making bonds. Whereas in energy releasing reaction, bonds are broken and then energy is released. 2.2 describes the amount of energy absorbed and released in chemical reactions, with reactants being the things you start with and the products being the things you end with in a reaction. What this particular slide describes is something called the activation energy. Activation energy is the amount of energy you need to start a reaction. There's an old adage, there's an old saying that says you need to put money or invest money in order to make money. Well, in a chemical reaction, there is a similar idea where you need to input some energy in order to get some energy out of a reaction. Now, if you look here, these are the reactants, the things we're starting with, and they have a certain amount of energy. And then the products here have less energy, so therefore the reactants have more chemical bonds and the products have fewer chemical bonds, because we are talking about chemicals, and energy and chemicals are stored in their bonds. But look what has to happen here. Let's follow the yellow line first. And the yellow line is the amount of energy you need to put into the reaction in order to get the reaction started. So this is here the amount of energy you need to put into the reaction. That's the activation energy without an enzyme. Now, an enzyme is something called a catalyst. It's a type of chemical called a catalyst. And a catalyst speeds up chemical reactions. Enzymes are just specific to living things. They're organic living catalysts that speed up chemical reactions. Without an enzyme, well, the reaction takes a lot of energy to start. So that means your body has to input energy in order to get that reaction going. But if you look at the red line, which is with an enzyme, you can see that the amount of energy needed to start that reaction is less. See, it's lower. Now, if the amount of reaction to start the chemical reaction is less, well, does that affect the products? Well, let's look at this graph. They both end at the same products. With the enzyme and without the enzyme, both ends at the same products, because that's one of the tricks to catalysts. They're not involved in the reaction. They simply make it easier for that reaction to take place, and they also make the reaction faster. So having an enzyme will speed up the reaction. It'll make the reaction easier, but it won't affect the reaction as a whole. And this is true of all catalysts. All right, chapter 2.2 talks about redox reactions. Redox reaction is a short way of writing an reduction and oxidation reaction. And the way I remember reduction and oxidation reactions is I use the term oil rig. OIL for oil is oxidation is lose. Now look at something that's being oxidized. You have an electron donor, it has an electron, and look what the electron's doing, it's leaving. So what you're left with at the end of the oxidation portion is something that has been oxidized. It's donated the electron. So if this is an atom, the number of protons and electrons are equal. It donates an electron, so this one now has the same number of protons and one fewer electrons. If you have one fewer electrons and the original number of protons, you have a +1 charge because you lost a negative. For a reduction reaction, we're using the oil rig. We're going to use rig. Reduction is gain. So this atom is gaining an electron. It has the same number of protons and electrons before. It gains an electron and therefore is reduced. It has an extra electron, so it has a negative charge. Now, positive and negative does not mean good or bad. What it does mean is how the pluses and minuses balance out in that particular atom or ion after this. So again, oxidation is lose, reduction is gain, and a redox reaction, one is losing, the other one is gaining, so they are coupled together.